Welcome! In this video, we are finding the last three non-zero digits of 90 factorial. I will take you through the steps for solving this challenging question. One reason to find the last three non-zero digits is that a calculator will not give you the answer. In line 1, let fk equal 10k plus 1 times 10k plus 2 and so on till 10k plus 9. 10k plus 5 and 10k plus 10 are omitted, which will be included later on. For example, when k equals 0, f0 will equal 1 times 2 times 3 times 4 all the way till 9, excluding 5 and 10. When k equals 1, f1 will equal the multiple of 11, 12, 13 till 19. 15 and 20 are omitted. Line 2 shows that the product of 10k plus 1 and 10k plus 9 is 100k squared plus 100k plus 9. The product of 10k plus 2 and 10k plus 8 is 100k squared plus 100k plus 16, so on and so forth. Line 3 shows the products of the first and last two terms from line 2. Now observe that except the product of 9, 16, 21, and 24, all terms resulting from the expansion of line 3 are multiples of 4,000. Line 4 shows that fk and the product of 9, 16, 21, and 24, when divided by 4,000, have the same remainder, 576. Therefore, fk equals 4,000 a sub k plus 576, a sub k being an integer. In line 5, let gk equal fk times 10k plus 5 times 10k plus 10, since they were excluded earlier. Now replace fk with 4,000 a sub k plus 572. After simple manipulations, like factoring and combining, gk equals 10 squared times 1,000 a sub k plus 144 times 2k plus 1 and 2k plus 2. Here, a pattern emerges. 144, regardless of the value of k, surfaces as the last three digits, excluding 2k plus 1 and 2k plus 2. I meant earlier 576. Line 6 shows 90 factorial equals the product of the gk's, k going from 0 to 8, and the result of combining those 9 terms. Excluding 18 factorial, 144 to the 9th will decide the last three digits. The b in the equation, like a sub k, is an integer. Line 6 also shows 10 factorial isolated from 18 factorial equals g0. Line 7 follows after replacing 18 factorial with g0 and the product of 18, 17, down to 11. Line 8 shows that 90 factorial has 21 zeros at the end. Finding the last three non-zero digits, we divide 90 factorial by 10 to the 21st, 144 to the power 10, and the product of those numbers behind decide the last three digits. Now a calculator can handle these numbers since they are small enough. In other questions in which numbers are large, we can apply Fermat's little theorem, which I will not be teaching you. In this question, the answer is 112. More explanations. Number 1. The first obstacle we face in this question is the zeros at the end of 90 factorial. Zeros are produced by 5s and 2s. Since there are more 5s than 2s, and 90 factorial has 21 factors of 5s, there will be 21 zeros at the end. Factorial is a big number. The key to solving this question is finding the pattern. Observing the products of 11 to 19 and 21 to 29, we see the individual numbers of both series have 1 through 9 as the last digits. We exclude 5 multiples since they make zeros with the 2 multiples. 5 multiples will be managed by factoring 5 out of the list, 5, 10, 15, 20, etc., and producing another sequence, 1, 2, 3, 4, etc., which can be dealt with the same way. Number 3. Why do we use 4,000 in line 4? First, observe 4,000 times 25 equals 100,000, and 576 times 25 equals 14,400. Then add those numbers. 144 makes the last three non-zero digits. Number 4. With these steps, we can find the last three non-zero digits of the factorial of any big number. Thank you for listening. If you enjoyed this video, there will be many more to come.